Good morning, everyone. My name is Sophia Cetrulo, and today I will be doing a presentation on the past, present, and future of antibiotic resistance and how we can look to nature to combat this deadly issue. So I would like to begin with a quote from Alexander Fleming, who originally discovered penicillin, which was the first antibiotic brought into market in 1945. This is a quote from his 1945 Nobel lecture in which he says, "The time may come when penicillin can be bought by anyone. Then there is the danger that the ignorant man may easily underdose himself and by exposing his microbes to non-lethal quantities of the drug make them resistant." This is important because even from the discovery of penicillin, we were aware that this was an issue and that antibiotic resistance would be quick to form with incorrect use of antibiotics. So to begin, bacteria and antibiotics. What are they and why are they important? So bacteria are prokaryotes. Those are the oldest known organisms on Earth. They are single-celled and they have no nucleus. They make up over half of Earth's organisms, with some studies estimating they make up about 90% of all organisms that we know. And each human themselves is inhabited by approximately 38 trillion bacteria. This is especially significant as each human has about 30 trillion human cells, meaning that we are outnumbered by microbial cells within our own body. So within our bodies, we have good bacteria. These bacteria are necessary for our survival, helping to regulate our gut microbiome, our digestion, our immune system, and our vitamin production. However, there are also pathogenic bacteria, and one of the things that make this pathogenic bacteria so dangerous is the fact that they can multiply extremely quickly. So, this video shows the process of bacterial division, which is known as binary fission. This can occur within just 20 minutes, meaning that within one day, one bacterium within our bodies can transform into 5,000 billion other bacterium. So, moving forward, what is an antibiotic? An antibiotic is the use of an organic compound to inhibit or kill a bacterial target. For the purpose of this presentation and a lot of common language, antibiotic is also used to refer to this specific organic compound. So these compounds are able to work because they target specific cellular processes or cellular structures that are found within bacteria, as you can see from this figure. So they will commonly target things such as the cell wall, DNA, RNA synthesis, folate synthesis, cell membrane, or protein synthesis. For an example, cell wall synthesis. Cell walls are specific to bacterial cells, not commonly found within human cells, and especially in bacteria known as gram-positive bacteria, which have those thicker cell walls. Without those, they are not able to form, they are not able to survive, and they are not able to replicate. So when that cell wall synthesis is inhibited, the bacteria are no longer able to survive and reproduce. But then there are also the methods of antibiotic resistance, which bacteria can evolve to counter these methods of antibiotics. So this includes efflux, which is expelling the antibiotic particles from the bacteria before they are able to work, immunity bypass and target modification, which prevent the antibiotics from working by either taking out the cellular processes that those antibiotics are supposed to target, or modifying the targets themselves so that the antibiotics are not able to bind to them and work. Antibiotics work somewhat like a key and lock system. If the lock is changed, the key will no longer work and antibiotics will be rendered ineffective. Similarly, with inactivating enzymes, it is as if there is a different lock that is used that prevents that antibiotic from working for its initial target, and the bacteria are not able to be targeted by the antibiotic. So I want to draw your attention to this, which is a giant petri dish containing E. coli. So within this petri dish, there are various amounts of antibiotics. This outer section has no antibiotics, so the bacteria are very easily able to grow. However, within each section, within this section, there is the normal level of antibiotic that would normally be able to kill bacteria. In here, there's 10 times, then 100 times, and in the very center, 1,000 times the normal level of antibiotic. You can watch as within this, the E. coli is able to grow and gain resistance to all of these different levels of antibiotics, going to being resistant to 1,000 times the normal level of antibiotic within just the span of 11 days. So this is very significant as it shows that this antibiotic resistance can very quickly form when E. coli and bacteria in general is able to gain resistance to these lower levels of antibiotics. So it is very, very, very important to highlight that antibiotic resistance has not been created by wrongful antibiotic use, but rather selected for unintentionally as these antibiotics were misused over time. What this means is we have found evidence of resistance genes within bacteria as far as 2.5 million years before human antibiotic use was even on the table. We did not have antibiotics to use against these bacteria for a very long time, and those resistance genes have existed. However, because of wrongful antibiotic use, we have selected for the survival of bacteria with this resistance gene, which has made them more present. So that takes us to past antibiotic use. So going back to the quote from Alexander Fleming and the misuse of antibiotics, humans have been using antibiotics for thousands of years. There is evidence as far back as 350 to 550 CE of human antibiotic use, as tetracycline has been found within skeletons in the Nubian desert. However, with the wrongful antibiotic use that was started from 1945 within what I will discuss is the golden era of antibiotics. So this is an era from the 1940s to the 1960s in which antibiotic discovery and thus antibiotic use greatly increased. You can see the discovery of penicillin in 1928, and it gradually increased to this large period within the 1940s and the 1960s in which 2/3 of all antibiotic classes were discovered, meaning over 20 antibiotic classes. So this is significant as with the increase of discovery of these antibiotic classes, there was a vast increase in the use of these antibiotics. However, we could not anticipate what we now face today, which is the discovery void in which only one new class of antibiotics has been discovered since 1987. So again, this leads us into present, in which in the last 38 years, only one new antibiotic class has been discovered, lariocybin. So this leads us to the causes of antibiotic resistance and why it has become such an issue from antibiotic use. So first is the overprescription of antibiotics. Over 90% of clinicians have felt pressure to prescribe an antibiotic when it wasn't needed or would not be effective, and 30% of all antibiotic prescriptions are incorrect in some way, whether that be duration, the type of antibiotic, or whether an antibiotic was needed at all. And there is also the issue of patients not taking the antibiotics as they are prescribed, if they are prescribed correctly. This is especially pertinent in the duration of taking antibiotics, as many antibiotics become effective before the entire duration of antibiotics is completed. So when you have a course of antibiotics that you would take for 7 days, if you only take them until day 5 and then feel better, there can still be a population of bacteria that can then be resistant to that 5-day duration of antibiotics. And when you go to treat them with more antibiotics in the future, it is ineffective. So there is also the unnecessary use of antibiotics in agriculture. It is estimated that 50 to 80% of the antibiotics that are produced are used specifically in agriculture and animal husbandry. It can help with growth, and it can be a sort of precursor and preventative medication for bacterial infections. But this can become a really big issue when an infection is created within these environments. It can be multi-drug resistant bacteria known as superbugs, which I will get to later. There's also an issue of poor infection control in hospitals and clinics, including long-term care environments. So that's not wearing personal protective equipment correctly and not maintaining a sterile environment. Also poor hygiene and sanitation practices, something we have become more aware of because of the COVID-19 pandemic, but in general, not staying away from people when sick and not hand washing or properly sanitizing hands. Then, I think, which is one thing that's very interesting and needs to be developed in the future, is the lack of rapid laboratory tests. This is especially pertinent because with bacterial infections, as you saw earlier, can multiply extremely quickly. And since these diagnostic tests and culturing this bacteria can take anywhere from 1 to 3 days, and in the case of fungal infections, sometimes weeks or months, patients do not have that kind of time before the infection worsens and can become deadly. So increasing the amount of rapid laboratory tests will allow for quicker diagnostics and more effective treatment in terms of knowing the type of infection that you're treating, the antibiotic you need to treat it, and the duration of the antibiotic that should be prescribed. So this also leads us to superbugs. There are 2.8 million antibiotic-resistant infections found each year. This is from a report by the CDC in 2019. They also put out a report in 2013. They started this report by talking about some of the positive impacts that have come from the implementation of methods, but then they go into how the issues have significantly worsened in some of the most extreme cases of superbugs that are posing a pertinent issue of today. So 2.8 million antibiotic-resistant infections each year and 35,000 deaths from those antibiotic-resistant infections. And the thing I would like to specifically highlight is the 124% increase of drug-resistant gonorrhea. So gonorrhea is the second most common STI in the world, and it has become resistant to almost every antibiotic we have thrown at it. We started with sulfa drugs, and the resistance was gained very quickly within about 10 years, and then on to penicillin, which is actually one of the least resistant, but it was no longer recommended for treatment in 1989, then tetracycline, azithromycin, and we are on our very last resort, which is two antibiotics known as ceftriaxone and cefixime. So we have gone through periods where cefixime was out of production, but this is currently the only antibiotic that is prescribed in order to treat gonorrhea, because we cannot tell if the gonorrhea is going to be resistant to all of these other drugs or not. So we are on our last resort. There is no other drug that is left to treat gonorrhea, and we have detected high levels of resistance to both cefixime and ceftriaxone. So once gonorrhea becomes resistant to both of these antibiotics, we have nothing left to treat it, and it can lead to things such as pelvic inflammatory disease and infertility. And again, to reiterate, it is the second most common STI in the world. People will continue to get infected, and these drug-resistant infections will continue to worsen. So one big reason for this increase in antibiotic resistance and also the lack of antibiotic discovery is the loss of resources. During the golden era, there were 11 big pharmaceutical companies that were invested in discovering new antibiotics, and now out of the 42 antibiotics that are currently being developed, only 4 of them are being developed by these big pharmaceutical companies. Many of these pharmaceutical companies have instead turned to heart medication or cancer research, as it is a much more profitable business. For example, with heart medication, 1 pill every day for the rest of your life, or your chances of survival worsen significantly, whereas with antibiotics, especially these new antibiotics and last resort antibiotics, you prescribe them as little as possible for at most a week, and you hope to never have that patient pay for the service ever again. So there's also a matter of cost for antibiotic discovery. It takes $50 million just to discover an antibiotic, possibly $1 billion to $2 billion more to put the drug onto the market, and there's a 95% fail rate for antibiotic discovery. So this has left a lot of medium and small-sized companies to face greater pressure for antibiotic discovery, but also consequently bankruptcy. So this leads us into the more hopeful future and some research that I was able to participate in over the summer. So one of the reasons I initially got invested in this project is because I was able to take a course at Brown University doing in-lab research, looking at the possibility of antibiotic-producing microbes within soil. All of these pictures are actually from the lab I worked at, and a lot of them are from my research. So we were able to, the top row shows the characterization and identification of different microbes from a soil sample, actually from Quinn's backyard. And then the bottom row shows the identification of the possible isolates, which are the bacteria inhibiting or killing microbes from those soil samples. Kind of as you can see on the escape assay, where there's like a little clear area, that indicates that this bacteria, where the one is, was able to kill the pathogenic bacteria above it. So this kind of leads us into the future and something known as the Tiny Earth Organization, which is an organization dedicated to collecting evidence of these soil isolates and creating this database that scientists are able to access. So this is a promising future because it shows that scientists can access a database of over 25,000 antibiotic-producing isolates. So it's a hopeful part of the future that soil research still holds many possibilities in antibiotic discovery, and there are many antibiotic-producing microbes that we have yet to discover. Another more innovative method of discovery for the future, or a method of countering antibiotic resistance, is the use of bacteriophages. So bacteriophages are viruses that are actually able to work against these drug-resistant bacteria, as you can see here, by lysing or rupturing the bacterial cells. So they are highly specific to the pathogenic bacteria. Oftentimes, antibiotics can mess with our good microbiome as they target bacterial cells, but bacteriophages are able to target these specifically pathogenic cells, which makes them an even more interesting area of discovery. And lastly, there is the introduction of deep learning AI. So as AI is expanding, there is a form called deep learning AI, which works more similarly to human thought, in which it is able to compound past experiences and put them forward into the method of discovery for drugs that we have not considered for fighting antibiotics, or drugs that we had previously used that could be more effective against antibiotic-resistant infections. So, in conclusion, antibiotic resistance is a pressing issue that continues to pose threats to the health of humanity, but by utilizing innovative avenues and looking at the natural environment, especially soil, there are many paths of antibiotic discovery to solutions in the future. Here's my works cited.
So again, not from the non-science person. I liked how you had certain aspects of your presentation, such as the timeline, which makes the presentation, easy to follow. I like that you cited certain reports, like the CDC reports over time. So again, mentioning these sources that you're using, these reports, these studies, which adds validity to your presentation, is super important. I like that you included the big pharma and the profit motive and sort of bringing in some of those political and economic factors to this alongside the scientific research aspect of it. Was really good. Super cool that you did actual research at Brown and being able to actually get into the field and do what these researchers are doing hands-on. I think that was really great. And then having that argument in your last slide, your conclusion, again, sort of reinforces like the main point that you're trying to prove. And I think a lot of times with research papers, students have difficulty sort of articulating what is your main argument in all this. And so that was very clearly stated, so I like that. I guess so my main question is this, I apologize, I came in a little bit late from the restroom, but is this antibiotic resistance affecting certain age or ethnic groups more so than others?
Thank you for your question. So it's very interesting that this is a problem that a lot of people consider to be less of a developed world problem, but there's actually a high correlation of antibiotic use and antibiotic resistance. As for age, so it's interesting, as antibiotics were introduced in 1945, so they have been accessible to many of the generations alive today. There is a lot of evidence of children taking many courses of antibiotics. I think it's like 10 courses of antibiotics before the time that a child is about 12, which is a very high amount, and so that's obviously more of a problem of resistance. But there is, actually it's very interesting, there's a lot of argument to be made towards global collaboration and global policy of trying to fight against antibiotic resistance, as in other countries. You can get antibiotics without a prescription. You can walk into a drugstore and just buy antibiotics, which leads towards a lot less responsible antibiotic use, as common people are not fully educated on the issue that may present. Yes.
Sophia, outstanding presentation. I learned a great deal, and so thank you for that. You mentioned, I think it's a test.
I'll go check, but I'm sure it is.
You mentioned that doctors felt pressured to prescribe antibiotics.
Yes.
I'm probably one that pressures my doctor quite a bit when I'm sick to do that. But did your research uncover any proof that doctors are slow to prescribe now because of the resistance?
So it's actually very interesting. There's a program that's being instituted in about 48% of hospitals known as a stewardship program, in which there are specific people in charge of overlooking antibiotic prescriptions and antibiotic use to make sure that they are effective. So the rates of antibiotic prescription have definitely slowed down, especially like when you go to the doctor and you have like a respiratory illness. It could generally be viral, especially if it's like a sore throat. It could be viral or it could be strep throat. So I think a lot of doctors now hold more precautions for that, and the stewardship program has definitely helped.
Thank you.
Yes.
So, an ignorant question, Spanish teacher.
It's okay. No, it's okay.
Why is the soil a good place to test?
So, it's actually very interesting. Soil is very microbe dense. One healthy tablespoon of soil can hold about, I think it's 50 billion microbes. So soil contains more microbes than it is such a valuable resource. There was research that for a long time there was a gold standard that we could only culture about 1% of soil microbes, but that standard has been changing, and with research investigations we think the number is much higher. So being able to culture millions, possibly billions of microbes, and every soil environment is different and contains different microbes. So that's why it remains such a good resource. Of course. Yes.
I have a follow-up on that.
Yeah.
So with the soil research, are they looking for new antibiotics? Are they looking for the way that different microbes are resistant within the soil, or how, like, what is that research?
So
what's the goal there?
specifically, I can go back to the slide. Specifically, especially with Tiny Earth Organization and like the soil research that I was able to do, it's looking for new antibiotics, possibly new antibiotic classes of things that are producing antibiotics that bacteria have not yet evolved resistance mechanisms to. Like with the new antibiotic that was just found, lariodicin, like that antibiotic class is the first antibiotic to target protein synthesis within bacteria. So it's something that, although the resistance gene may exist for it, it is not yet widespread enough for bacterial infections. Of course.
I'm allergic to tetracycline.
Yes.
Why did that happen?
So, I'm going to be honest with you. That was not something that I delved into within my research. I suspect it could be, as tetracycline targets certain processes, then it just might be that your body has an adverse reaction to that target and your cells may react negatively to that. It could be that your immune system recognizes the specific tetracycline molecule as something that could be harmful to your body, and so it's having that adverse reaction. And I'm not reacting well to it. Those are my speculations, but I do not have concrete research. I apologize.
You might have been able to be treated for acne with their tetracycline. Usually it's a normal protocol. Sophia, this is, I've said to you when you presented in front of me earlier, I think that this presentation is exceptional. The research is excellent. The fact that you were able to do research hands-on is also really important. Your delivery has been very fluid, and your ability to respond, to me personally, on a series of questions when you and I talked, were just extemporaneous questions, was outstanding. So I've been very, very impressed with the amount of work that you put into this and your passion for this topic. And I'm going to just ask you to sort of follow up to this. Is something that we talked about. We talked about several issues with this topic, and I think this is such a critically important topic, as you and I talked about, because you and I discussed how people can't imagine what it would be like to go back to a world pre-antibiotic. Many of us wouldn't be sitting in this room without antibiotics. We forget how we get treated for things with antibiotics and with minor cuts and all sorts of things. But anyway, the issue that I referenced to you is the incentive motive to find new antibiotics, because again, the drugs that are being researched now for cancers, those are expensive drugs. $4,000 for some kind of injection. There's not that level of incentive. I get antibiotics at Publix for free, and so the reality is, how do we change that issue in this conversation that's ongoing in the medical community? How are we going to incentivize drug companies to want to spend the capital and reap the returns in order to provide this essential tool in our toolbox to keep us alive?
So this is actually a very interesting issue. I discussed this within my course at Brown with my fellow students, with my instructors, with my TAs, with Ms. Buckley in our meetings about my project. And there's a number of solutions that are possible. There is obviously monetary incentive in terms of giving monetary sort of prizes to companies that are able to discover these new antibiotics. One big thing that's been brought into conversation is governmental interference into antibiotic research, because the government has the capacity and the funding to continue research on these antibiotics. Ultimately, though, it is It's a very hard question because, again, people can't imagine a world without antibiotics, and this problem has been going a long time. I have seen like fully put together reports from 1995 talking about this issue. Alexander Fleming warned about it in 1945. CDC made several reports in 2013, 2019. It's a continued issue. Money is one of the biggest barriers to continued antibiotic discovery because it is so expensive, because it has such a high fail rate. So monetary prizes, government, and then also there are policy solutions and incentivizing these organizations that could be instituted.
Thank you.
I had that question too, as I said, who should fund antibiotic discovery? And we've talked about it, and it's interesting. And I'm just wondering if we can use circ RNAs in any sort of way to combat these bacteria and stop them from replicating. So you and Matthew, you know, just go and do some research in undergrad and go on to do your doctorates, and then, like, you know, 15 years later come back and present.
We were able to characterize our bacteria by looking at one of the ribosomal subunits and some of the ribosomal DNA from there. So I wonder if there's a possibility of looking at RNA and the solutions that may lay with that.
Yes. That's so exciting.
Thank you, Sophia.
Thank you.